In 2010, physicists at the National Institute of Standards and Technology took two of the most precise atomic clocks ever built and placed one on a table while raising the other just 33 centimeters off the ground, about a foot higher. The clock sitting higher ran faster, and the difference had nothing to do with mechanical error or calibration problems, because time itself flows at a different rate 12 inches above your desk. Most people assume they understand what time is. You check your watch, I check mine, we stand next to each other, and the readings match. That comfortable assumption guided humanity for thousands of years, until Isaac Newton made it official in his Principia back in 1687, declaring that time was absolute, universal, and mathematical. Newton described a cosmic metronome ticking identically for every particle in existence, whether that particle sat on Earth or hurtled through the void between galaxies. Newton got it wrong, spectacularly and demonstrably wrong, and the proof isn't locked away in some particle accelerator or hidden in theoretical physics journals. The proof sits in your pocket right now. Your head ages faster than your feet at this very moment. The neurons firing in your skull experience time at a slightly faster rate than the cells in your toes. And over an 80-year lifetime, your head will have aged about 90 billionths of a second more than your feet. That measurement isn't metaphor or poetry, because NIST confirmed it with clocks sensitive enough to detect the difference across the height of a human body. The question nobody asks is what a clock actually measures. Most people assume a clock measures time the same way a ruler measures length, but a ruler doesn't create length, it compares one length to another. A clock compares something too, and that something is this invisible thing flowing through our lives that we trade for money and claim we're running out of. The assumption that time exists external to us, ticking away whether we observe it or not, turns out to be completely false, and the man who proved it couldn't even land a teaching job. Before the story of how we know this, the weight of what got overturned deserves attention. For more than 2 centuries, Newtonian physics worked flawlessly, predicting planetary orbits, explaining the tides, letting engineers build bridges and cannons and steam engines with perfect reliability. Newton's framework succeeded so completely that by the late 1800s, some physicists believed the fundamental work was essentially complete, with just a few minor details left to clean up. One of those minor details would tear the whole edifice down. The year was 1,905 inches. Bern, Switzerland, and a 26-year-old patent clerk who had been rejected by universities and worked a day job reviewing other people's inventions was about to demolish humanity's understanding of time. Albert Einstein had no fancy laboratory, no graduate students, no research grants. What he had was a desk, a pen, and the courage to take a simple question seriously, asking himself what it would look like to ride alongside a beam of light. The question sounds almost childish, but Einstein knew something had broken in physics, and it had been broken since 1887. That year, Albert Michelson and Edward Morley ran their famous experiment trying to detect the luminiferous ether, which was the invisible substance everyone assumed. Light must travel through the way sound travels through air. They failed completely. No matter which direction they pointed their apparatus, no matter how Earth moved through space, light always traveled at the same speed. The result made no sense under Newton's framework, and physicists spent 18 years pretending the problem would go away. Einstein refused to pretend, and he asked a different question altogether. His question was simple. What if light genuinely travels at the same speed for all observers, not as an approximation, but as a fundamental law of the universe? The implications of that question change everything. Picture yourself standing still while I zoom past you at half the speed of light, and a beam of light passes both of us. Under Newton's physics, I should see that light moving slower relative to me because I'm chasing it. Michelson and Morley proved that doesn't happen. Both observers measured the exact same speed of 299,792,458 meters per second, always, with no exceptions ever recorded. The only way the math works, the only way light can register at the same speed for observers in different states of motion, is if space and time themselves bend and flex. Time passes at different rates for different observers, and distances contract and expand depending on how you're moving. The universe preserves the constancy of light by sacrificing the universality of time. Einstein's former mathematics professor, Hermann Minkowski, heard about special relativity and immediately grasped something Einstein himself hadn't fully articulated. In 1908, Minkowski declared that space by itself and time by itself were doomed to fade away into mere shadows, and only a kind of union of the two would preserve an independent reality. He named that union space-time, describing 4 dimensions woven together so tightly that changing one always affects the other. This isn't philosophy or interpretation, because we've measured it with extraordinary precision, and the proof orbits above your head right now. 24 GPS satellites circle Earth at about 20,200 kilometers altitude, each carrying atomic clocks accurate to billionths of a second. For GPS to tell you where you are, to guide your car to the correct highway exit, those satellite clocks need to agree with ground clocks to within about 20 nanoseconds. Any more drift than that and your position becomes inaccurate by meters, then hundreds of meters, then kilometers. The satellite clocks don't naturally agree with ground clocks, and they never can, because time passes differently up there. Two effects work simultaneously, and this is where the math turns beautiful. The satellites move at about 14,000 kilometers per hour relative to Earth's surface, and according to special relativity, moving clocks tick slower. That effect alone would make the satellite clocks lose about 7 microseconds per day compared to ground clocks. But the satellites also sit farther from Earth's center in a weaker gravitational field, and according to general relativity, which Einstein completed in 1915, clocks in weaker gravity tick faster. That effect adds about 45 microseconds per day. 7 microseconds lost to velocity and 45 gained from weaker gravity produce a net result where GPS satellite clocks gain 38 microseconds daily compared to clocks on the ground. Without relativistic corrections programmed into every satellite, GPS would accumulate errors of about 10 kilometers per day, and within a week, your navigation system would become worthless. Every Uber ride, every Google Map search, every airplane landing relies on Einstein being precisely correct. The same theory that seemed like impractical abstraction in 1905 now underpins the infrastructure of modern civilization. A patent clerk's thought experiment about chasing light beams turned out to be essential for landing a 747 inches fog. The applications go deeper than navigation. Your smartphone performs relativistic corrections thousands of times per day. And the chip inside that enables location services isn't just measuring satellite signals, but compensating for the fact that time runs differently in orbit than it does in your hand. Every food delivery order, traffic check, and social media location tag runs Einsteinian physics silently in the background, adjusting for the curvature of space-time. Wall Street doesn't advertise this, but high-frequency trading firms pay millions of dollars to position their servers microseconds closer to stock exchanges. They're not just buying speed. They're buying a different position in space-time, and in relativistic terms, the trader whose server sits closer to the exchange occupies a slightly different temporal reference frame. Finance has weaponized Einstein. The abstract becomes biological when you look at what happened to actual twins. Astronaut Scott Kelly spent 340 consecutive days aboard the International Space Station, orbiting Earth at 27,600 kilometers per hour, while his identical twin brother Mark stayed on the ground. NASA studied them obsessively with blood samples, cognitive tests, and genetic sequencing before, during, and after the mission. When Scott returned, he measured as slightly younger than Mark, not by much at about 5 milliseconds over nearly a year, but the biological differences registered as real and detectable. Scott's telomeres had lengthened, his gene expression had shifted, and his gut bacteria had changed. Some of those changes persisted for months after landing. 5 milliseconds sounds insignificant until you multiply that by faster speeds and longer durations, and that's when the scenario worth serious consideration emerges. A spacecraft traveling at 90% of the speed of light to a star 10 light years away, and then turning around to come back, would complete a round trip that takes a little over 22 years from Earth's perspective. The traveler inside that spacecraft hasn't aged 22 years, though, only about 9.5. The traveler returns to find their twin 12 years older than them, and their children could have aged past them entirely. That's not speculation, but the math and every experiment ever run confirms it. Testing this happens with subatomic particles called muons, which get created when cosmic rays slam into our atmosphere. Muons decay quickly with a half-life of about 2 microseconds, which means 2 millionths of a second. Creating them at the top of the atmosphere about 15 kilometers up, simple calculation says most should decay long before reaching the ground, because the math is straightforward and they shouldn't survive the journey. Ground-level detectors pick up far more muons than that calculation allows, far more than the equations predict. The explanation is that muons move at nearly light speed relative to us, and from our perspective, their internal clocks run slow, stretching their brief lifetimes long enough to complete the journey. From the muon's perspective, the distance to Earth's surface contracts and the atmosphere literally shrinks in the direction of travel. Both descriptions work correctly, both represent reality, and that's what relativity means, with different observers, different measurements, same underlying physics, and consistent results. In 1971, physicists Joseph Hafele and Richard Keating strapped cesium atomic clocks to seats on commercial airplanes, with some flying east and some flying west, then compared them to identical clocks on the ground. The eastward and westward clocks disagreed with each other, and with the ground clocks matching Einstein's equations exactly. The universe operates this way, whether anyone finds it comfortable or not. The territory gets genuinely disturbing from here. Gravity in Einstein's framework isn't a force at all. at least not in the Newtonian sense. The sun doesn't reach across space and grab Earth with some invisible hand, but instead warps the space-time around it, and Earth simply follows the straightest possible path through that curved geometry. That path happens to trace an orbit. Dropping a ball doesn't mean a force pulls it down, but rather that the ball follows the straightest possible path through space-time curved by Earth's mass, and that path leads to the ground. Gravity is geometry, and geometry affects time as much as it affects space. In 2015, the Laser Interferometer Gravitational Wave Observatory, called LIGO, detected gravitational waves for the first time in human history. These ripples in space-time itself came from two black holes spiraling into each other 1.3 billion light years away. Einstein predicted gravitational waves in 1916, and humanity needed a century to build instruments sensitive enough to detect distortions smaller than 1/10,000th the diameter of a proton. The waves arrived exactly as the equations said they would, space-time ringing like a struck bell. Kip Thorne, one of the physicists behind LIGO, spent decades insisting humanity would eventually hear the universe this way, and the 2017 Nobel Prize proved him right. Thorne served as scientific consultant on Interstellar, and that scene where the astronauts visit a planet near a massive black hole and experience years passing in hours was scientifically accurate. Time runs dramatically slower in strong gravitational fields, and close enough to a black hole's event horizon, a few minutes for one person could stretch into decades for someone watching from a safe distance. Reversing this direction and traveling to the past remains an open question. General relativity permits mathematical solutions called closed time-like curves, which are paths through space-time that loop back on themselves. Some involve wormholes, which are hypothetical tunnels connecting distant regions of space-time. Some require exotic matter with negative energy density, which is something never observed. Some involve the infinite rotating cylinders of a Tipler machine, or the frame-dragging effects near spinning black holes. Stephen Hawking proposed the chronology protection conjecture, suggesting that the laws of physics conspired to prevent anything from traveling into its own past. Every time physicists find a mathematical loophole allowing backward time travel, some other physical mechanism seems to close it. Proof remains elusive, and this stands as one of the deepest open questions in physics. Unlike forward time travel, which amounts to ordinary motion through space-time at varying rates, backward time travel would require something never demonstrated to exist. The thought that still unsettles me comes next. If space-time forms a four-dimensional fabric, then your entire life from birth to death exists as a complete geometric object. Physicists call it your world line, a path through 4 dimensions that constitutes your existence. The version of you that was born, the version reading this now, and the version that will someday die all represent different points along the same structure. Some physicists take this very seriously and call it the block universe, or eternalism, which is the idea that all moments in time are equally real. Einstein himself struggled with this concept. When his closest friend Michel Besso died in 1955, Einstein wrote to Besso's family saying that Besso had departed from this strange world a little ahead of him and that this meant nothing. People like us, who believe in physics, Einstein wrote, know that the distinction between past, present, and future is only a stubbornly persistent illusion. That letter deserves a second reading. Einstein wasn't offering spiritual comfort, but stating what he believed the physics implied. Dead loved ones haven't ceased to exist, but instead exist in a region of space-time that the living cannot access. The past isn't gone, and the future isn't unwritten, because they're all laid out in the 4-dimensional block, and consciousness simply moves along its world line, experiencing one slice at a time. Whether that's true remains unknown. The block universe interpretation carries implications for free will, for choice, and for what it means to be alive. Not everyone accepts it, and the equations don't specify which interpretation is correct. They just describe how space-time behaves, and space-time behaves in ways that make the question impossible to dismiss. Neuroscience adds another layer worth exploring here. Your brain doesn't experience time directly, but constructs the sensation of now from signals that arrive at different moments. Light from your environment hits your eyes, while sound waves hit your ears, and pressure sensors fire in your skin, all traveling at different speeds and arriving at your brain at different times. Consciousness stitches them together into a coherent present moment that doesn't physically exist. Every person always experiences the past, running a few hundred milliseconds behind reality, while the brain smooths over the seams. Humans don't perceive time directly, but hallucinate a version of it. The beautiful irony is that human brains evolved on the African savanna, where relativistic effects were utterly irrelevant to survival. Nothing in evolutionary history prepared humans to understand that moving faster makes time slow down, or that standing near a massive object makes your clock tick differently than mine. That's why this feels wrong, and why the gut rebels against it. Human intuition evolved to track zebras and avoid lions, not to comprehend the geometry of the cosmos. What remains to carry forward from all of this is straightforward. Time is not what anyone was taught. It is not absolute, not universal, not the same for everyone. It curves around mass and dilates with velocity, woven into space so completely that discussing one without the other becomes impossible. Every flight of stairs climbed is a fast forward into the future by femtoseconds. Every highway drive slows the driver's clock relative to someone standing still. Everyone is a time traveler, just a very slow one. Einstein figured all of this out by sitting quietly and asking what riding a beam of light would look like. No particle accelerators, no space telescopes, just a patent clerk with a thought experiment and the courage to follow the mathematics wherever it led, even when it led somewhere that seemed impossible. Time is not a river flowing outside of you and not a cosmic clock ticking somewhere in the void. Time is the geometry you move through, and how you move matters, and where you stand matters. Your experience of the universe is genuinely, measurably, physically different from mine, even when we stand in the same room. Telescopes become time machines when pointed at the sky. The moon appears as it looked 1.3 seconds ago, because that's how long light takes to cross the distance. The sun appears as it looked 8 minutes ago. The Andromeda Galaxy, which is our nearest large galactic neighbor, appears as light that left 2.5 million years ago before Homo sapiens existed. The Hubble and James Webb telescopes, pointed at the most distant galaxies, observe the universe as it existed just a few hundred million years after the Big Bang. Astronomy becomes cosmic archaeology, looking at the past rather than the present. The night sky, the clock on your wall, the fact that you're getting older at this very moment, all of it connects. All of it traces back to Einstein. All of it reveals a universe so strange and so precisely structured that a thought experiment from 1905 still predicts phenomena discovered today. The common mistake about time is thinking it's simple, thinking it's universal, thinking that reading a watch means understanding it. Time is the fabric of existence itself, curved and stretched and personal and profound, and everyone is woven into it whether they understand it or not.